So I just have 4 slides, kind of for the benefit of people like myself who are not super expert on Byzantine fault tolerance, and just so there's a common dialogue before these guys get into the nitty-gritty. All right, so what's Byzantine fault tolerance? It's the study of systems, often distributed systems, in the presence of faults. One can imagine, hardware failures, or a network with a network composing of a lot of interacting entities, some of which are compromised. Both would fall under Byzantine fault tolerance. It's a hard subject. Theoretical models of how to deal with this stuff are not generally agreed upon, sort of unlike other areas of computer science. So you do need correctness proofs, because somehow if you launch one of these technologies, it will find the state in which things are broken, but you won't catch it in testing. And yet, it's full of false proofs. It's very easy to convince yourself that something works when it doesn't. Okay, so some keywords: safety and liveness. Safety is a property that something bad will not happen. It's an invariant property. Liveness is a property that something good will happen. Maybe something good will happen eventually. And usually you're trying to prove 2 separate statements with different methods in this field. Essential notion: synchronous versus asynchronous. Synchronous roughly means the participants in such a system can coordinate times. Maybe there's a notion of rounds, or they have clocks that they can synchronize. Asynchronous is just the opposite. A lot of algorithms use state machine replication. So you can imagine to create redundancy, and this is sort of the approach that Bitcoin uses, although Bitcoin is not a client-server model. You take whatever sort of algorithm you're intending to implement that might fail and just replicate it massively. And you see that idea over and over again. Historical results: so the Byzantine generals problem, that's also Lamport. He's done sort of everything in this field. It's a synchronous model for consensus formation. I think we've all heard of it. So generals must decide, whether they go in and attack or not. They send messages to each other, but they can't necessarily trust the messages. How can they decide whether they should do this or not do it? It's resolved in certain cases. Another interesting result: the FLP theorem says in a fully asynchronous system with just one faulty process, it's impossible to achieve consensus as you would in the synchronous Byzantine general context. Finally, Byzantine fault tolerance was sort of computationally intractable in the fully asynchronous or mostly asynchronous case until the paper Practical Byzantine Fault Tolerance came out. I think it was the late 90s, it is a state machine replication approach. All right, and we'll let them talk in just 1 second. So Byzantine fault tolerance and cryptocurrency. So Bitcoin, the blockchain, is described in some sense as a solution to the Byzantine generals problem. Maybe it's an engineering solution. It's got a probabilistic component to it, but I think it's an accurate description. Finally, there's a framework that's starting to become popular. Some people at the University of Texas are working on it, among others, called the Byzantine sort of altruistic rational fault tolerance framework, where Byzantine sort of nodes or network participants can fail arbitrarily. Altruistic participants they follow a protocol exactly and honestly, so to speak. Rational participants will try to maximize their economic value in participating in a network or system or protocol. So maybe this is a framework that we can try to analyze cryptocurrencies within. And with that, let's open it up. And we'll hear from, I guess, Jaquan first, since he has the mic. So,
Hi.
Maybe first question. So, to what extent is cryptocurrency just Byzantine fault tolerance with voting power determined by mining or stake?
To what extent is what? That?
So the modeling that we do in cryptocurrency on consensus, is that the same as Byzantine fault tolerance, where instead of replicas that are faulty or malicious, voting power is just determined by stake, and we can think of them as replicas that are faulty or malicious?
Mm-hmm. Yeah, so traditional Byzantine fault tolerance algorithms had been focused on processes, so discrete units of machines, as if they were individuals, right, like people. They were counted, integers. But for cryptocurrencies, and looking at the way Bitcoin works, I think we're more comfortable with the idea of fractional voting power. So, you know, anybody with a small amount of stake or mining power can participate and feel that they're contributing, or it's fun. You know, it gets people involved in it. It gets and it makes it more secure overall. So it's adapting. At least Tendermint, and yeah, all of the cryptocurrencies are adapting the results from Byzantine fault tolerance research into the non-integer fractional realm.
To play devil's advocate, suppose you have very little hash power and you will really never win a block. Could we then imagine the system as discretized? And does your argument still hold?
Yes.
Okay.
Yeah, you know, in practice, for Bitcoin, if you have like a very small miner, then it's fine. Like, you'll never mine a block. You bought like a small lab heater, great. But in proof of stake, it can get unwieldy if everybody is allowed to vote, even with minute amount of stake. So in practice, we'll probably see some sort of mechanism of a threshold amount of stake needed to participate.
I think maybe. So I think it's when talking about conventional Byzantine fault tolerance, we really need to be very precise. So when considering this field of study in the context of cryptocurrencies, it's very important to realize that something where you have voting in a chain is very, very different to conventional consensus. Conventional consensus brings a group of nodes to universal consensus and agreement in a single step, maybe in a series of rounds, but there's a protocol that brings those nodes at the end of the protocol to agreement. That's very different to a system where people are, adding their signatures or hashing power to blocks, and these blocks are being added to the end of a chain, and you might say that after some number of blocks have been added, that, in some kind of Monte Carlo system, we're kind of slowly approaching consensus. That's very, very, very different. It's important to remember this, that, conventional, traditional Byzantine consensus works with a group of nodes that have individual voting power. They perform some protocol, and at the end of that protocol, they either agree or they don't. And there are a bunch of assumptions that go into making these protocols work. You have different network models. You have a synchronous network model where you can assume all messages are delivered within a certain period of time. You can have a partially synchronous network model where the assumption is that the network may play up for a period of time, but after some maximum period of time, it returns to a synchronous behavior. Or you can have an asynchronous network where no timing assumptions are made whatsoever. And that's just one of the first assumptions that you have to decide on. And at the end of all these things, you end up with a mathematical proof that shows that your algorithm will always reach a conclusion if a certain proportion of the nodes are what you call correct or good, if you like. The theoretical limit within a synchronous network is that once an adversary has 1/3 of nodes, that's it. You can't reach consensus. And within this, and it's actually a branch. I mean, Lamport started the whole branch off with the Byzantine generals problem in 1982. But it's been a very, very active area for research. And right now there are, computer science professors around the world who've dedicated their entire career to studying Byzantine Consensus. And it's a very, very sophisticated and involved area of computer science. And the reason that this hasn't been applied so far within cryptocurrencies is very simple. It's because we haven't found a solution to the Sybil attack. That's all. The only reason that we have the blockchain is because it was a solution to the Sybil problem. That's the only reason. It's a far inferior consensus system to a conventional consensus system if you take that away. And if you notice with the Bitcoin blockchain, there aren't any nodes. There are no individual nodes. Voting is performed using hash power. Your voting is proportional to hash power. There's no notion of an individual node performing any kind of task whatsoever within the actual algorithm at all. And that's how Satoshi got around the Sybil problem. The Sybil problem is where an adversary comes along and he decides to upset the network just by introducing a load of fake nodes, right? So you can imagine if you have a voting system, right, and you make it like everyone in this room, right, decides they're going to vote to make some decision. An adversary comes along, he wants to upset our voting process, he just stuffs the room with lots of extra people. And now all of a sudden, the voting's unbalanced and the adversary can win. So what Satoshi did, that's the Sybil problem. So what Satoshi did is he said, right, we're going to get rid of voting and nodes altogether. We're just going to have the ability to add a block relational to the actual hashing power. And so when looking at all these algorithms, the first thing to think about is, how can we apply them? Is there a way that we can address the Sybil problem so that we can actually have individual nodes within the network that are able to participate within these algorithms? And once you do that, if you can find a way of addressing the Sybil problem and giving nodes secure identities, then all of a sudden there's a vast, accumulated science of Byzantine fault tolerance and consensus that can be applied within cryptocurrencies. And I think what's going to happen in the coming years is we're going to see a merger of the two different branches, if you like, of consensus, which is the traditional branch of computer science that deals with Byzantine consensus and the kind of sort of blockchain iterative approaches. Yeah.
Can you guys talk a little bit about what you have personally taken from traditional Byzantine fault tolerance and used in your projects, maybe at a somewhat high level?
Sure. When I started working on Tendermint, I was looking for a forkful model that kind of was similar to Bitcoin in that I tried to find a way to come up with some kind of monotonically increasing value for each blockchain or something so that everybody can quickly identify the best blockchain, and that's how agreements will be made. And everything I tried to come up with wouldn't work. So what I mean is I had this scaffolding of the blockchain and this incentive not to fork it once there is a blockchain, but I couldn't come up with a way to decide on the next block. And so that was the piece that was missing, and I found the solution in traditional research from a paper from 1988. So the way Tendermint uses Byzantine consensus is iteratively. It happens at every block, and it runs this round-based protocol. Hopefully it completes in one round, but if needed, it'll go on until it reaches consensus. And then it uses that to decide on the next block, right? And then that block goes onto the blockchain, and then it'll do it again and again and again.
So in my case, I sort of took some time off just to study conventional Byzantine consensus, which I think was, worthwhile in the project I was pursuing. I was very lucky to come across a paper by a French professor who specializes in Byzantine consensus. And he used a technique that allowed me to derive another Byzantine consensus protocol, which is fully asynchronous, which means it doesn't have any timing assumptions. And it's leader-free, which means that none of the individual nodes orchestrates consensus, which is very important, because if you have a node that orchestrates consensus, it can be attacked. Just like if you have timing assumptions, it can be attacked. So going back to Leslie Lamport's Paxos, you may have heard of Paxos. It's used by Google's Chubby system, and some it's quite popular in distributed computing. And there's a Byzantine fault tolerant variant called practical Byzantine fault tolerance. That's a leader driven algorithm where a leader is elected from the group of nodes, and it kind of orchestrates the other nodes and takes them, guides them to consensus. So I worked on an algorithm that's leader-free, so all of the nodes participate equally. So there's no individual node that you can attack to stop the protocol proceeding and concluding. But it's also uses something. It's what's known as a randomized consensus protocol. So Kieran mentioned something called the FLP impossibility result in his presentation, and this is a very important result in computer science that says that if you have an asynchronous network, i.e. where you can't make any timing assumptions, if only a single process, i.e. a single node, a single server in your network fails, you can't be sure that the remaining nodes will be able to reach consensus. So the way around that is to design a protocol which terminates with probability approaching 1, if that makes sense. And randomized protocols do this, but for a randomized protocol, you need something called a common coin. And a common coin is nothing to do with coins and cryptocurrency. It's a common source of randomness, which turns out to be very, very powerful. But where I think this gets really interesting is that you'll notice that one of the things that a blockchain does very well is produce a global source of randomness, right? In the sense that you can't predict who's going to solve the current puzzle, who's going to find the hash with that number of leading zeros. So blockchains produce a global source of randomness, and that can be fed into these asynchronous randomized Byzantine fault-tolerant consensus protocols. And that's very promising. So one of the areas I'm looking at currently is using a global blockchain as a source of randomness, which is used to organize my network. And within those smaller organizations, conventional consensus is used, and it uses the blockchain as a source of randomness. And there's all kinds of innovation happening at the moment in conventional Byzantine consensus. So in fact, the French professor whose work I originally used to derive my own work, he's coming up with some new things that are in the works at the moment, and we could have a probably common coin, right? So I think that comes back to, I think that we're going to see a kind of we're going to see interesting combinations of this kind of new Nakamoto consensus and its derivatives and conventional Byzantine consensus, and that's where the real power of decentralized networks will be realized. And I think we're going to see that using these combinations, decentralized networks can scale out and also be very, very highly performant as well. So this whole idea that you can't have a performant decentralized network will be shown to be very wrong indeed, and we'll have decentralized networks that perform faster than some of our centralized services in the end. So I think it's an exciting area.
So maybe one more from me before we open it up. Jay sort of alluded to earlier, and then Dominic mentioned the idea of the Sybil attack and the sort of Bitcoin makes no identity or transparency assumptions. If you were to encode in a protocol level a stronger notion of identity or maybe federation, would it be a lot easier to use traditional BFT? Are there any problems with that idea? Speak.
I'm not sure I understand the question.
Sure.
So in Tendermint, for example, it's pseudonymous, and it's not. It doesn't enforce identity, so like public identity of a person or an operator of a validator. It's just pseudonymous, kind of like Bitcoin addresses. So if you have a public key address, then assuming that it's secure, then only you are able to sign messages using it. And that is sufficient for Tendermint's security. Now, if you add identity on top, so that, let's say, a validator is also associated with a real world identity, and maybe that was entered onto the blockchain, I think you can do even more, and perhaps make it even more secure, and it's worth considering.
So I think the question is if we can add a kind of security layer within which nodes can identify themselves, does that make things easier? And the answer is yes, because the whole problem with centralized computing, the whole problem with applying these conventional Byzantine fault-tolerant protocols within decentralized computing is the Sybil attack. The whole reason for all of the work that Satoshi did is the Sybil attack. Everything comes down to the Sybil attack. So everything we can do to anchor the identity of nodes and make it difficult to create nodes is beneficial in that respect. So the Sybil problem is actually quite a difficult and subtle problem, because we might imagine that somebody can just pay some stake to join the to join a node to the network, and that's a sufficient solution. But the trouble with that is it's just a payment upon entry. There's no continued application of resources necessary. So that's the answer is yes. Something like CertCoin, which is a decentralized identity system that's being proposed, would be very useful. People would have to invest some time and some resources in order to create an identity for their node before it participated. And if the node misbehaved, it could be expelled from the network. But the Sybil problem is quite a deep and subtle problem, and I think there'll be work ongoing to address Sybil attacks for many years. But I think there are some good solutions coming out on the way to coming out at the moment.
Yeah. So I learned about all of this through Bitcoin, and it's very hard to imagine for me and maybe other people in the audience, like, what are problems where there isn't a Sybil problem? Like, I'm surprised there's such a large body of work where the Sybil problem is ignored. If you have some centralized entity, why do you even need a mechanism to achieve consensus rather than that centralized entity calling the shots?
One easy example is if you've got a bunch of servers that you all own, but they're physically in different locations. So you know that they're trying to do the right thing, but they might just fail randomly. Or I suppose one person could maliciously compromise one of them, maybe someone, a disgruntled employee or something like that. So there's no Sybil problem there because you have a couple servers that just know to talk to each other only.
Yeah, I think the network you're talking about is more of a centralized network. So decentralized networks, in theory at least, are open to anybody. The idea is that anybody can join the decentralized network. And in fact, as processors leave the decentralized network, it's possible that new entrants replace them even, right? So yeah, it's true. If you have, you own a hosting room in a hosting center and you fill it with your own servers, you don't have to worry necessarily about the Sybil problem. The Sybil problem really comes into play with decentralized networks. But what I would say is that I think in the coming years, we're going to see a lot of enterprise systems, which are traditionally centralized, moving to decentralized architectures, because it allows security to be managed more economically. And within and then you do get back to the Sybil problem, because the disgruntled IT employee might want to break the system for some reason or other, and he might just fire up a whole bunch of spare PCs in his office or something, right? And so at the moment, at least, anyways, though, it's something really that applies to decentralized networks, although possibly to centralized networks in the traditionally centralized applications in the future.
Yeah. So the way Sybil nodes are taken care of in Tendermint is you require a collateral deposit before you can partake in the consensus process. But for other applications that start off centralized and it's not about the currency, you could say adapt Tendermint so that there's no need to like send coins because it's not about the coin, but you could assign weights or voting power to nodes centrally and give them relative weight as to how secure they are, say, for example. And you can just use Tendermint that way.
Maybe, yeah, one more. We're over, but we started late. Anybody?
Any other questions? If not, I can add a little something. So Pebble is what Dominic is working on, and Tendermint is what I'm working on. And it's interesting because there are only so many ways to overcome the FLP impossibility result that we know of. One is assuming partial synchrony of time, or another would be having a common coin. So we're taking both approaches, and yet we're different in our approaches. So that's pretty interesting. So, like with Pebble, I believe it uses. So going back to what I was originally saying with like the fractional presence of voting power, and it's not discrete. It's not so much the case in Pebble, right? Because it is based on discrete numbers of processes and thresholds, multi-signature, cryptographic threshold signatures. So it's not always true.
So I think that it's important to make a distinction between your consensus process, and there are two levels to your consensus process. One is the process by which the chain is built, and one is the process by which agreements reached on individual blocks, which is using a conventional Byzantine Consensus algorithm. And that surely must be treating actors equally, or not? Is it an adaptation of the original system? Is there a proof for it?
No, that's because I'm terrible at writing proofs. And I just know that I'm not good enough no matter how hard I try, because writing proofs is hard. So somebody else should do it for me. And maybe it'll turn out that Tendermint is flawed, and then I would like to know as soon as possible. But yeah, in Tendermint, it's not discrete units. Rather, maybe everybody posted like 1 unit of coin, and everybody's equal. But then one guy posted like 0.1, and then his voting power is only a tenth of everybody else's, and it still works because it doesn't use like cryptographic threshold signatures, which require that kind of discrete division. Rather, it's done in a naive way where it counts the votes and tallies it up very naively. And that's sort of it's also where the power comes from and the flexibility.
So the question is, can anybody explain what happened to Stellar? And I can explain what happened to Stellar. So one of the issues with conventional Byzantine fault tolerances is quite a complex field, and there's a lot of ways you can go wrong, which is why that you have to have quite rigorous models, and you should ideally have mathematical proofs that things are correct under various assumptions. And Stellar didn't make assumptions, assumed a synchronous network model. And what that means is they assumed that, amongst other things they shouldn't have assumed, they assumed that messages would always be delivered within a certain period of time. So, if you don't receive a message from some node in Stellar, in the old Stellar system, you were able to assume that the node that was sending it had failed. And that's not how the internet works, right? Actually, the internet is asynchronous. You can never really know how long it's going to take to send a message, and somebody might DDoS you and delay your message, right? So there was that and a few other things, but it was mainly that they didn't handle asynchrony correctly, and they got punished by their consensus algorithm failing and a fork.
Just a quick follow-up. So how come Ripple doesn't have the same?
Ripple does. So in fact, after the, I was predicting the problem would occur, and amongst other people, I think, and once it did occur, I think Ripple went back to a single validator node. So it's not really a decentralized network, it's a centralized network. There's a single validator that's orchestrating all consensus. But there's a guy called David Mazieres, who's, I think he's head of secure systems at Stanford, and he's working on a new algorithm for Stellar, and I would have thought that Ripple will just return the favor and fork it back and adopt Stellar's new consensus algorithm when they have it finished.
I don't know everything about what happened, but this is sort of what I've deduced, and it may be incorrect. But I think that Stellar had been running an experiment where it was adding a lot of nodes, and unlike Ripple. So I think there were more validators in Stellar's network than in Ripple's network. And the thing about the Ripple consensus algorithm is that it works if you have a tight and small topology, but depending on the shape of the graph, its ability to handle asynchrony and latencies is limited because it's mostly based on consensus at the local level, and then global consensus is sort of tacked on top. So the reason why Ripple, I don't think Ripple reduced to one node. I think they still have, Stellar reduced to one node after the attack, and then Ripple remained their tight network. So it works for Ripple because they have more centralized control over the topology. But it works for Ripple because it's a different use case. They want to control that network.
I think that should wrap it up. Thanks.